it's Miss Christie here. I've got a question sent by a student on rigid bodies. It's a really nice question. There was one slight mistake with the question. It didn't specify what mu is, so I've put it in there. You can see it there. And I'm just going to do a little quick recap of what you would typically do in a moments problem. It's going to be very informal. It's not super mathematical, but if we follow this procedure for basically any rigid bodies problem, as long as we've got the correct forces and we know where to take moments from, etc., we'll be okay. So the 3 steps that you typically follow, step 1, is because it's an equilibrium or limited equilibrium in general, let's say, the resultant moment about any point is 0. And so the way I write this, and again it's not very formal, is that the clockwise moment is equal to the sum of clockwise moments is equal to the anti-clockwise moments about any point. Typically I teach this as taking moments about the most complicated point, which I'm going to tell you which point that is here, and then it's going to turn out that we're not going to do that for this one. The second thing I'm going to do, and third thing, are the sum of forces, of all the forces, the resultant force on the rigid body, on the rod, is 0. And the way we could say that is up is equal to down, so resolving vertically in this situation and resolving horizontally. But it doesn't necessarily need to be that. It could also be resolving perpendicular to the surface. So in this one it would be like this, right, perpendicular to the surface, and resolving parallel to the surface, which would look like, let's say, like this, right? So decomposing that way. This will make sense in a second. Okay, so those are the 3 things, and typically we do it in that order: moments first, and then equilibrium stuff involving forces afterwards. Okay, so let's read this question and put some forces on my diagram. So a uniform rod means the center of mass is going to be going through this center of mass 5 kilograms and length 8 meters. So I've got 5g, not 5g acting here straight down, and you can put alpha here, the angle that's there. Length 8 meters, so this will be 4 meters. I'm going to use green for distances. So the A to M, let's say, is 4 meters. So this distance, let's put it here, is 3 meters, and this distance is 4 meters. If you've got a 4-way pen, it's quite useful here. The rod is held in rough horizontal ground. I kind of skipped that, so we know there's friction. Limiting equilibrium is key. Limiting equilibrium means the friction is equal to the maximum friction, right? So friction is equal to Fr max, which is mu r, right? So we know what friction is mu r. And there's the ground it's in contact with. And so here's your ground. The normal reaction will go perpendicular to that surface. Normal reaction, of course, so it's perpendicular. Let's do that again. It's going to go like this. And then we have a force. Which way does it want to slide? It wants to slide this way. So we have friction going towards the left, let's say, and we're going to call that mu r. And they told me in the question, just read ahead, that coefficient of friction was 2/3. So we know this is 2/3 r. Let's put that on my diagram. They tell me tan alpha is 3/4. So if tan alpha is 3/4, I'm just going to write over here. If tan alpha is 3/4, we can draw a little triangle. We know alpha is an acute angle, so we can just draw a little triangle like this. Opposite, adjacent, hypotenuse. We can get sine alpha, we can get cos alpha. So 3/5, and cos alpha is 4/5. We'll come back to that in a second. Okay, distance A to C is 1 meter, and it's held, what does it say here? Okay, the angle between the rope and the rod, so here's the rope and the rod, is beta, and the tension in the rope is T newtons as shown in the figure. The coefficient of friction, we already read that, we skipped ahead to see that bit. The vertical component of the force exerted on the rod by the ground is R newtons. Okay, so that's the normal reaction. Okay. So, now, it says find the value of R. Now, typically, I would tell students, take moments from B because that's the most complicated point. Basically, when you take moments about a particular point, we know that moment is force times perpendicular distance, and if you take moments at B, those 2 forces will disappear from your equation. However, we want to work out R, and what's more complicated about this is that we've got this angle beta involved, and we don't know what the angle beta is, right? And so we've got 2 unknowns here, T and beta, and so it's actually better to take moments from C, so we can generate an equation that eliminates T and beta from that particular moments equation that we're going to form. So I'm going to take moments from C, which is not orthodox, right? Typically we take moments from B. Just want to make that clear. So taking moments from C, So moments about C. In fact, let me just rub this out because we're going to come back to this stuff anyway, right? Let me just rub this out. And then I'm just going to move this stuff up. Right. So taking moments from C. So moments about C. And I will, we have to talk about a couple of things here. The first thing is, okay, if I'm going to take moments about C, I need to work out, there's two ways I can do this. I can do force times distance, or I can do let me make this clear. I'm going to decompose my forces with respect to the rod. So I'm going to use purple here. I have 5g cos alpha. I have 5g sin alpha going this way, but I'm just going to put it here. So 5g sin alpha. And then, just to make this clear, the length of the arrow does not represent the magnitude of it, because otherwise, I mean, I could make this one a bit smaller, but I don't actually know what t is and stuff like that, so it's not really a good idea, but I think it helps if I just do this. And now what I'm going to do is decompose these ones, so I'll make this clear. So I'm going to decompose the 2/3 r with respect to the rod, so I'm going to get the parallel component and the perpendicular component, which I'm going to put here. So this is 2/3 r cos alpha, and this is 2/3 r sin alpha. I've also got an angle alpha here, right? So if that's not clear, there's alpha. This will be 90 minus alpha because this is 90 degrees. And then this is also 90 degrees because this is perpendicular parallel, right? These are perpendicular to each other, so that's 90. So if that's 90 minus alpha, that must be alpha. And again, I'm going to break this up, so I'm going to use a different color here, otherwise it's going to be kind of confusing. So let's use green. So I have r cos alpha going this way, and I have r sin alpha there, but I'll just put it here, but it's going to be a bit confusing, so maybe I'll just leave it here, r sin alpha. Okay. Now, this is important. Why did I break this up? Any force parallel to the rod is not going to generate a moment. I think this makes sense because think about it. If you have a rod and you apply a force parallel to it, it will not generate any rotation. And when we talk about moments, we're talking about rotation, right? And so this, the 5g sin alpha, the 2/3 r cos alpha, and this r sin alpha, which I've put up here, but is actually over there, are not going to generate any moments, so we don't care about those. And so we're just going to focus on the 5g cos alpha, the r cos alpha, and the 2/3 r sin alpha. So which ones are clockwise? Well, we'll show you in a second. So a common question I get asked is, how do you determine what kind of moment a force is generating? Is it a clockwise moment or is it an anti-clockwise moment? Well, one way you can determine this is, well, first of all, let me just show you what we have here. We've got the diagram drawn on this board, and in orange you can see the forces from my previous diagram. This 5g cos alpha I'm interested in is the perpendicular component of this 5g. It was in purple before. This 2/3 r sin alpha is the perpendicular component of the friction force, and this r cos alpha is the perpendicular component of the normal reaction force over here. Okay, and so all of these are going to generate some kind of moment. The parallel ones, as we said previously, do not generate any moment. And what I'm going to do is put my pen here, and if I apply, so I'm fixing the point here. If I apply this 5g cos alpha, which is going this way, to this pen at this point, it's going to rotate in a clockwise direction, which means that this force will generate a clockwise moment. Similarly, this force here, if I were to apply it here, and by the way, I can't extend it there, but you can imagine do the same thing, it would generate a clockwise moment, this 2/3 r sin alpha, whilst this r cos alpha would generate an anti-clockwise moment, and that's what you can do to determine it. Taking moments from C, I'm going to do 3 times 5g cos alpha. So this is a clockwise moment I'm doing. So 3 times 5g cos alpha. 3 times 5g cos alpha. And then I have this distance, 7 times 2/3 r sin alpha. Is equal to 7 multiplied by r cos alpha. And then I can find r from this if I just do a bit of rearranging, right? So we've got 15g, I'm just going to leave it like this. So that's going to be 14/3 7 over 3, let's see, it's 15g cos alpha, let me just work this out, plus 14 over 3 r sine alpha equals 7r cos alpha. Divide everything by cos alpha, so I don't need to use these two basically. I get 15g plus 14 over 3r is equal to tan alpha is equal to 7r, and that gives me 7r minus 14 over 3 multiplied by 3 over 4r is equal to 15g, and that's 7 over 2, so 3.5, so 3.5r is equal to 15g. Therefore r is equal to 30g over 7. I'm just going to leave it like that because it didn't specify after giving it a particular form, but if I use 9.8 then I must run my answer to 3SF, but it should come out nicely anyway because 9.8 over 7 is quite a nice number. There are two options here. Option 1 is to resolve, so I have to deal with the equilibrium situation in terms of forces. I can resolve parallel and perpendicular to the rod, or horizontally and vertically. In fact, I should have said that the other way around, because horizontally and vertically is typically the way we do it. Now, you might argue parallel and perpendicular would work out here, and it would because you've already decomposed your forces in that manner. And so all you need to do is decompose the final force and have t cos beta and t sine beta, which you can put there. But because this is mechanics and we can give our answers to 3 significant figures, we don't really need to do that. What we could do instead, and it's a bit easier to do this, is to break up this force horizontally and vertically, which I'm just going to put here. Right, you can put it there as well if you want. And what we can use is the fact that we have alternate angles, right? If that's alpha, this is alpha, and this angle is beta minus alpha. And so what I have is that this component is t cos beta minus alpha, and this component is t sine beta minus alpha. And again, we're not dealing with exact values here, so we don't need to worry too much. We don't need to basically use compound angle formulae later on. And this makes it a lot nicer because now I can just do resolving vertically. And I'm going to ignore the green and orange forces, just the red, because the green is the decomposition of R, right? It's just the components that make up R. And the purple ones here are the components of the mu R, 2/3 R, and these are the components of 5G. So just ignore them now. And vertically, I have t sine beta minus alpha going upwards. I also have r going upwards, so plus r, which is the r from before, is equal to going downwards 5g. So I get t sine beta minus alpha is equal to 5g minus 30g over 7, which is 5 over 7g. Right? So that's my first bit. And then I'm also going to resolve horizontally like this. Right? And I get t cos beta minus alpha is equal to 2/3 r. That's the only one. Remember, we're only dealing with the red forces here. 2/3 r. And so I've got these two equations, and I can, plug in. This is equal to what 2/3 times that. So that's 20 over 7g. And then what I could do is divide equation 1 by equation 2 to get tan beta minus alpha. Right. So t and t cancel. So I get tan beta minus alpha, again, t over t, sine over cos, and the angles are the same. So you get tan theta, tan beta minus alpha, is equal to 5 over 7g divided by 20 over 7g, which the g's cancel. I'll write it down, otherwise it's not super clear. And that's going to give me a quarter. And then I can just do arctan of a quarter. And then I can bring in the alpha from before, right? So that's the key thing. And it's okay because we're dealing with in mechanics we can just give answers to 3SF. So arctan of a quarter, I'm in degrees. It's 14.0324. I've got 6 there. ... And then beta is equal to 14.03624 plus alpha, and alpha you can get by doing arctan of 3 over 4. So it's just tan. 3 over 4. So I'm just going to do that quickly, and that should give me my final answer, and that's 50.9 to 3SF. There we go. There's our final answer.